So we are starting our meeting for today, our class for today, continuing up from where we ended. We are still looking at mechanical properties of matter. Yes, we see that last time we looked at tensile stress and tensile strain, and this has come up on where we are saying tensile strain. Yes, we looked at tensile strain, and then we said, of course, that tensile strain is the strain due to tension in a cord or in a particular material. When we apply tension in that material or substance, we get to produce some strain, meaning some change in length. And we looked at some formulas that are used to relate pressure, or should I say stress. When we induce stress in an object, we can cause some strain, and the relationship is Young's modulus. So keep that in mind. Even when you're answering your multiple choice questions, you should have that information on your tiptoes, or on your fingertips. Actually, on your fingertips, you should have that information. So and we looked at some Young modulus. So whenever we talk about Young modulus, we are talking about tensile stress and tensile strain, connecting, referring. So you can't use other constant of proportionality. The only constant of proportionality which is used when we talk about tensile stress and tensile strain is Young's modulus. And it is just a measure of how hard is it to stretch an object. So if they ask in the multiple choice, what is tensile strain? What is Young's modulus? You will just be looking at the measure of how hard it is to stretch an object. All right, stretching it, trying to change its length by stretching it. How hard is it? That measurement is called Young's modulus. So today we are looking at another interesting property of matter, and today we'll be looking at elasticity of shape. So elasticity of shape, will just be talking about changing the shape. All right, so obviously it's not changing it in terms of maybe it was previously a sphere and then maybe you change it into a ball. No, it's, for example, it's still a sphere, but what are you doing to that sphere?
Sir, can I ask a question before you start solving?
Yes.
When I was watching the video that you sent on YouTube, you never finished solving the question. I don't know whether you sent another one, but I never saw it. The meeting ended.
Yeah, the meeting ended because, in fact, I forgot to record the other part. Okay, so but go through it. Actually, the good thing is, even in the notes, when you go through the notes, you find that they are very simple to follow. And then when you're following through the notes, and then you find something challenging in the notes, that then you can ask me. Yeah.
Okay,
so
thank you.
Awesome. So we are looking at elasticity of shape today, and you discover that the same concepts that we applied on tensile strain, we'll apply them again on elasticity of shape. It's only that here, in elasticity of shape, we are trying to change the shape of an object by shearing it. All right. So when we talk about elasticity of shape, what we have is, for example, if when we look at this object, which is here, this object is a rectangle, but when we apply a shearing force, we tend to make it into something like a rhombus or so. Something like a rhombus or so, if I've not confused my shapes. So what is happening here? The difference between tensile strain and elasticity of shape is that, let me just show you on the diagram of tensile strain. The force that we're applying perpendicular. Let me even be drawing something so that you see what I'm doing. So here, this force, all right, this force which is here, it is perpendicular to this surface. Have you seen this surface which is there? Yeah, this surface is in the y-axis, but the force is in the x-axis. So the force that we're applying in tensile strain is the force which was perpendicular to the surface. All right, but now the difference with what we are doing today is that, just a moment. Yeah, so the difference with what we are doing today is that today the force is being applied parallel. On top there, we saw that the force was being applied perpendicular to the surface, meaning if you are, for example, here would have applied a force at 90 degrees, maybe trying to stretch it up this way. But then, have you seen this surface which is denoted as A, area here? So with elasticity of shape, in this case is that, with the elasticity of shape, we'll be applying a force parallel to this surface. When we apply a force parallel to this surface, obviously we also expect that this surface, this block should not be moving, should be fixed on the surface, on the ground, by maybe some friction force or something like that. So that's why you are even seeing another force which is pointing us in that direction. Good morning, Simbarashe. Simbarashe, are you with us? Good morning. Okay. So, hope you'll be able to respond. But what we are talking about is that, let me just remove this, which is here. What we are saying is that with elasticity of shape or shearing mode, or what we call shearing force, we apply a force parallel to the surface area, and we expect that this shape that we're trying to shear should be fixed at some point. Maybe it should be fixed by some force which is in equal to magnitude with the shearing force. So as you can see, the negative force and the shearing force have the same magnitude. It's just that they are pointing in different direction. The reason why they should have the same magnitude is that to make sure the summation of forces in the x-axis is equals to 0, such that this object should not be moving. So we don't want this object to move from this point to that point. We want it to be fixed at one point. But the forces, one is acting on the down surface here, another one is acting on this upper surface, so that as we apply a force like that, and this surface will have, this shape will have some height, like that. But then from the original point, you see that this corner here on top here has been shifted by a delta x. I hope you guys are seeing what has happened here. So this surface or this corner was on this position, but it has been shifted by a delta x by this force. So now we are going to try and find out how we can manage to do calculations with regards to such situations. And at this point, I would like to find out if you guys are okay with what I've explained so far.
Yeah, it's just okay.
Yeah. Yes, sir. Yes, sir.
We are okay with the explanation so far?
Yes.
Awesome, awesome. Simbarashi, are you with us? Just a moment. So yeah, like I was saying, we have explained on how elasticity of shape is all about, or what elasticity of shape is all about. So one of the important things to remember is that in shearing stress, the applied force, as we have said, is parallel to the cross-section area, all right? Whereas tensile stress, in tensile stress, we looked at that the force was perpendicular, was making a 90 degrees with the cross-section area. So now, even just the same thing that we also talked about when we were dealing with tensile stress, we said that we talked about stress being equal to force over area. Even here, shearing stress is also the same. That surface area where the force is applying, you just divide the force, divide by the area, you get your shearing stress. And we also have what is called shearing strain. So what shearing strain is just the ratio of this change in length here, the one which is written delta x. The shape was here, but it has moved to that shape. The change in length over the height, h, all right? That is what we refer to as shearing strain, all right? And the formula is right here. Shearing strain is just that delta x over h. Sometimes you may be given a cube, sometimes you may be given a rectangle. So I'm sure sometimes they will draw a diagram for you, or even if they don't draw a diagram, you have to be able to visualize a diagram, draw it, and then look at which one is your height and how much change in x or change in length is showing up. Okay. Yeah. So with that said, we are also talking about the relationship between, we say this is shearing stress, force over area is shearing stress, and the delta x over h is shearing strain. Yeah. So we see that there is a constant of proportionality, S. And this constant of proportionality is called shearing modulus. So we have to be able to differentiate these things. We know that we are dealing with different things here. When we talk about shearing stress and shearing strain, the relationship is needed. Sorry? So, someone had a question? Okay, maybe your mic was accidentally on. So we are talking about...
Sir, the new person can't get you.
Sorry?
The new person, I don't know the name, can't get you.
I texted him. So let's see if I can text him again and say, join in audio. He is supposed to join in audio. So yeah, we are talking about shearing stress, and we have said that it is related to shearing strain by this shearing modulus. Again, what we can say about shearing modulus is that it is the measure. So this shearing modulus, it is the measure of how hard it is to shear an object. All right. Excuse me. So we expect that an object with a larger shearing modulus, all right, an object with a larger shearing modulus, just like the example which I gave on, okay, let's see. Yeah, just like the example which I gave on the last point, the last chapter when we were, the last topic when we were looking at tensile stress. I gave an example to say, for example, if you have copper and iron, say iron, in this case, for example, let's say iron has a shearing modulus of 1000 Pascal. That's copper has a shearing modulus of 1000 Pascal. Let's just give that as an example. And then iron has a shearing modulus of 2000 Pascal. Which one would you think would require a larger force to shear it by the same shearing strain? Which one would you require a larger force? Quickly.
We said that the one with a higher modulus thing, the one, yeah. So 2000.
The modulus thing. I thought we are calling it modulus, shear modulus. It's not a, yeah. So Simbarashe, you are able to hear us now.
I'm able to hear now.
Okay. So hopefully you'll be able to catch up. And if possible, we are recording this video so you can be able to still look at it at some other point. So let's look at an example to see how we can, yeah. So let's look at an example. I'm sure you'll be able to, sorry?
All right.
Awesome. So let's look at an example from the tutorial sheet to see how we can appreciate this concept. So let us have Florence to read for us this question here, where it's starting from 2 parallel and opposite. Yeah, Florence to help us read this question. Florence, are you there?
Oh, I was taking better. It's me reading.
Here. Starting with 2 parallel.
Okay. 2 parallel and opposite forces, each of 4000 Newton, are applied tangentially to the upper and lower faces of a cubical mantle block, 25 centimeter on each side. Find the angle of shear and the displacement of the upper surface relative to the lower surface.
Awesome.
Shear modulus for the metal is 0.8 times 10 to the power 11 Pascal.
Awesome. So, like I said earlier on, when you're reading a question, try and read it twice or 3 times so that you make sure that you understand the question. So, let's look at a diagram to see if we can actually visualize what they're saying. We see a diagram here. I had to draw it with my pen. We see that there are 2 forces, 2 parallel forces. And I would like to just note that this is not 400. This is also supposed to be 4,000. So take note of that. So this is 4,000 in this direction and 4,000 in that direction. So what we have is that we have 2 parallel and opposite forces each of 4,000, all right, are applied tangentially to the upper and lower faces of a cubical metal block. All right, so we have a cubical metal block. We expect that all the sides are the same at 25 centimeter. So they are applied tangentially. What they mean by tangentially is that they are applied in parallel to that surface. All right, the surface and the force are parallel. That's how it is. So now this is a cube. Its original shape was this shape, which you can see in bold blue lines. But then after applying this force, the other one, which you can see faint in there, is the resulting effect. The resulting effect of applying these two parallel forces caused the change in length. And actually, they have been asking us to find the angle of shear and the displacement of the upper surface relative to the lower surface. So what is the angle of shear? The angle of shear is this. So we expect that from the original position to where this surface has moved, there'll be some angle. We would need to measure that angle. And how can we measure that angle? So that's what we are going to see in the part of the example on the solutions. So this is the data. We have forces 4,000. The height should be given in meters. And then we have the shearing modulus that we don't know the angle. We don't know how much it moved. So let's look at the way we are going to appreciate this. If we want, what we can do first of all is to find the value of the change in length with relative to the other surface. So we find this change in length. All right. So how can we find this change in length? We have to look at the formulas that we have. What formulas can we use? And of course, after we find a change in length, then we can apply trigonometry and say that the change in length, we would expect that if we find this change in length and we know this height, which we can call L or length or height or anything, we can apply trigonometry to find this angle. This length is adjacent to this angle. That change in length is opposite to that angle. So we can use tan and say tan theta is equals to the change in length over L. So first of all, we need to find the change in length. All right? Yeah. So we see that how can we find this change in length? We use the formula that we talked about earlier on. So this is shearing stress. Shearing stress is equals to, okay, let me just mute the mic of our friend who is, okay. We are saying that shearing stress is equals to shearing modulus multiplied by the change in length over the height. All right. And so we need the area, right? We need to compute the area. And we know that the area of a surface, or for example, of a cube is just multiplying the length times the other length, which are the same. So it's just a matter, since we're given that each side, the lengths are 25 centimeters each. So we can just multiply 25 by 25, we get our answer. And this is because it's a cube. We expect the faces to be the same. Now, using this formula, we can find change in length to be the subject of the formula. And then finding change in length to be the subject of the formula, with the information that we have the force, we have the height, we have the area, we have the shearing modulus, we can find the change in length to be 2 times 10 to the power minus 7. All right, it's a very small change, but it's significant especially some of you guys who go to engineering, you discover that when you're trying to do fit in one object into another object, if the one object has changed in its length, you find that when you try to fit in them, you find that it will be hard because of those changes in length. So we have found a change in length, and change in length is 2 times 10 to the power minus 7, and this is in meters. All right. So, and then from there now we can find the angle. All right. We can find the angle. As we said earlier on, that the shearing angle, remember they told us to say find the shearing angle. And the shearing angle is this part here. They said find the shearing angle, and the shearing angle is that part. And we see that we can compute tan theta is equals to x, change in the x over the length. And since we have found a change in x, we'll put it on top there. We've found this value. We'll put it on top there. And we know that the original length, or should I say the height, this part here, the height, since it's a cube, we were told that it is 25 centimeter, which is 0.25 meters. And then we can compute the angle like that. So we have found what they were asking us to find in that question. Are we okay on that, with that solution?
Yes.
Yes, sir.
I have a question, sir.
Yes, yes.
Yeah, you can go just on the drawing there, the one which you drew.
Mm-hmm.
Yes, sir. So it means for shear, yeah, this is here. For shearing, we find the surface area, meaning on top there, the area on top there.
Yes.
And then for stress, it's the area on the side, the right side there, the surface of the right side there.
Okay.
It was stress.
Okay. Let me explain a bit there. Yes, you are correct in a way, but one thing that we have to remember is that for shearing, of course, we are looking at this surface which is on top here. The reason why we are computing the area of this surface which is on top is because that's where the force is being applied. We can't use this area here because this area is not where the force is being applied. So in fact, stress is the force over area. So this is the force and the area is that area. All right. And then we have been told in the definition for shearing stress is that the force has to be parallel. So meaning it has to be in the same direction, in the same plane with the surface area. So the force is parallel to this surface area. But if we are talking about tensile stress, this force was not going to be parallel. This force was going to be at 90 degrees to this surface, probably pointing upward, even pointing downward, because there's also negative tensile strain, meaning it is compressing the object. So, but if it is trying to stretch the object, we would expect that the force would be up and the force would be, let me just see if I can draw something. So the force would have been pointing in that direction, all right? But the same area which we were going to use was this same area, all right? That would have been for tensile stress, all right? We're talking about tensile, all right, due to tension, all right? Yeah, so that is when we talk about tensile stress. But for shearing stress, we have seen that we use the force which is parallel to this surface, and the force which is, and the surface is here and the force is there. So are we okay now?
Yes, sir.
Awesome.
Another question, sir.
Yes, yes.
Yeah, what if the forces are applied on the same surface? I mean, like on the same surface, if they are applied downward or upward, the parallel forces are applied. How can be the answer?
If this 400 was also on top there.
For sharing. Yes.
Yeah, meaning there will be no net force on
Can
top
there
here.
be a sharing?
No, there can't be a sharing, because imagine if we are holding hands, all right? You are putting that way, me, I'm putting this way. Nothing will do nothing. We'll cancel out each other. So, but the thing is, if one is putting on the ground here, the one who is putting on this ground and the one who is putting on top, on the ground, he just wants to make sure that this object stays intact, it doesn't move. But the one which is actually doing the shear is the force which is on top there. So the force, this one keeps the object intact, and this one tries to shear the object.
All right.
So are we okay now with this part of the property?
Yes.
Mm-hmm. Yeah. What about the others? The others are quiet. Are we okay with the solutions that we have shown?
Yes, yes.
Yes.
So now I want to see the answer. I don't know whether you had put it to the inverse of the term. I'm only seeing 8 times 10.
Here, 8 times 10 to the
This
power
one.
minus 7. 8 times 10 to the power minus 7.
Yes, you forgot. I think you forgot to do this. Add this one
To do what?
to find the inverse. Yeah, tan inverse.
Oh, I forgot to find tan inverse. Ah.
Yes.
I see, because, oh yeah, theta is supposed to be, since we are saying arctan, because we want to find theta, we have to do arctan. And then what we have here is that we only have 2 times 10 to the power minus 7 divided by 0.25, which is the 8. So yeah, you can actually do that even when you be going through the solution and find the tan inverse actually. Yeah, I don't know why sometimes when I'm typing fast, I get to forget some of these things, but thank you for noticing that. Thank you for noticing that. And there's another one with a question. Okay, so without wasting much of the time, let's look at also the other concept, which is volume elasticity. All right, so some of these things that I'm telling you guys is that I think one thing that I want to show you guys is physics is not challenging. All right. One thing that I would like to, in fact, maybe I'll say this after after we have gone through the whole class, so that I show you that physics is just like a puzzle, playing with numbers. They say calculate this, so you find out how can I find this given this information. And I want you guys to realize and see that physics is one of the most beautiful courses. The beauty in it is that it describes physical, the physical reality, and the physical reality is intuitive, meaning even without getting a pen and paper, you can already think about it and even make thought experiments. And also even before you write an equation, it should come from your mind, how you have thought about what the question is. Sometimes even when you find an answer, you even ask yourself, have I gotten it correct? Because your mind is telling you that, no, this is not the way it's supposed to be. So the formulas that you use are just there to mirror what is in your mind. So even when you're talking about tensile stress, tensile strain, you know exactly, even in your mind, you know it, that when you apply a certain force, for example, like what we have been talking about, when you apply a certain force on a surface, obviously this surface will move in that direction, and there'll be a change in length. And then you would also realize that if that force over area is equals to the shearing stress, and we have been given the constant of proportionality, this constant of proportionality is just a measure of how hard is it to shear that object. All right, how hard is it? And then we have also been told that after you apply that shearing stress, you expect some change in length. All right, change in length over the height, which is the strain. You expect some strain in that object. So even when you are going about doing your calculations, these things are ringing in your mind. It's not like you are just punching the calculator, you have mastered the formula. It's not like that. These things have to be internalized in your mind. Is that okay?
Yes.
Yes, sir.
Awesome. So obviously this link, the time is saying it will go out, but then we'll come back and just quickly finish up on because the last part which we're looking at is just this volume elasticity, and you guys should be good to go on your quiz on Friday. So sorry?
The quiz has been moved.
Oh, has been moved, eh?
Yes.
Okay, maybe we'll have a quiz of our own. I'll try and prepare some questions tomorrow to give you guys to see if you can do something concerning this topic that we have looked at. So one of our friends have left, but like I'm saying, the meeting, the time is going to elapse, and then you guys will go back to the link, and so that we can just finish up on the last part. Yeah. So otherwise, when we come to this other topic, which is volume elasticity, by volume, you expect that volume is the capacity of that container, right? The capacity of a container, the capacity, or